We look up at a night sky filled with pinpricks of ancient fire, finding comfort in the patterns they weave across the darkness. For as long as we have been sentient, we have used these lights to navigate, to tell stories, and to ground ourselves in a seemingly infinite landscape. Yet, our biology has conditioned us to focus only on the signal, the glowing gas and the burning cores of distant suns. We rarely consider the space between them. We assume that dark is merely a stage, a passive background waiting to be filled. But as our gaze extends further into the cosmos, we encounter regions where the signal disappears entirely. There exists a place so vast and so profoundly empty that it defies our fundamental understanding. How the universe organizes itself. It is a silence that stretches across hundreds of millions of light-years, a hole in the fabric of the observable world. To look into the Boötes Void is to confront a scale of nothingness that the human mind was never designed to process. We are forced to ask if this emptiness is a natural byproduct of creation, or if we are witnessing a phenomenon that suggests our maps of reality are missing their most critical piece. To understand this void, we must first learn how to see the nothingness itself. The universe, as we understand it, should not be capable of forgetting. Every cubic meter of space carries within it the memory of its own creation, a faint echo of energy, a distribution of matter refined across billions of years. From the moment of the Big Bang, matter has expanded, cooled, and clumped into the galaxies, clusters, and filaments we observe today. The assumption underlying all of modern cosmology is that this process was fundamentally uniform. Variations exist. Of course, local densities differ. Gravity sculpts regions into stars and voids, but on the largest scales, the cosmos should be smooth, predictable, isotropic. This is the cosmological principle, and it is not merely a hypothesis. It is the foundation upon which we have built our models of universal expansion, dark matter distribution, and the fate of everything that exists. And then there is the Boötes Void. In 1981, astronomer Robert Kirshner and his colleagues were conducting a redshift survey of galaxies in the constellation Boötes. They were mapping the three-dimensional structure of the universe, measuring how light from distant galaxies had stretched as space itself expanded. What they found was not a cluster, not a filament, not even a modest underdensity. They found nothing, a spherical region of space, roughly 330 million light-years across, containing almost no galaxies at all. Where thousands should have been, there were fewer than 60. It was as if someone had scooped out a portion of the universe and left behind only darkness. To comprehend the scale of this absence, consider a thought experiment. Imagine the Milky Way, our galaxy, home to hundreds of billions of stars. The only island of light humanity knew for most of its history, placed at the center of the Boötes Void. From that vantage point, looking outward in any direction, we would see nothing. No neighboring galaxies, no Andromeda spiraling toward us, no small satellites orbiting our galactic halo. For 165 million light-years in every direction, the night sky would be a featureless black. The nearest external galaxy would be so distant, so faint, that even with the most powerful telescopes of the early 20th century, we would not have detected it. Humanity would have grown up believing we were alone. It would not be until the 1960s, with the advent of radio, astronomy, and deep photographic surveys, that we would have had the tools to glimpse the truth. That beyond this vast emptiness, the universe continues, populated and structured as expected. But we do not live in the Boötes Void. We live in a region where galaxies are plentiful, where the cosmic web is visible, where the universe looks roughly as it should. And that is precisely why the void is so disturbing. It exists not in some remote corner of the observable universe, but within relatively nearby space. It is not a relic of an earlier epoch, nor a boundary condition at the edge of observation. It is here, now, unmistakably real, and it should not be. The cosmological principle tells us that if we zoom out far enough, the universe should appear homogeneous. On scales of hundreds of millions of light-years, the distribution of matter should average out. Galaxies cluster, yes, but voids and clusters should balance each other in a predictable statistical pattern. The Boötes Void, however, does not fit this pattern. It is not merely a region of lower density. It is an absence so profound that its probability, given our models of structure formation, approaches the implausible. If the universe began in a near-perfect state of uniformity, the fluctuations in the cosmic microwave background represent the seeds from which all structure grew. Then how did such a colossal region remain so barren? The initial reaction among cosmologists was one of cautious skepticism. Voids were known to exist. The universe is not a uniform fog of galaxies, but a web of filaments and walls, separated by enormous empty regions. But the Boötes Void was different. It was larger, emptier, and more spherical than anything previously observed. Its very shape suggested something unusual. Voids typically form through gravitational dynamics matter, clumps together along filaments, leaving behind underdense regions in between. But this process produces irregular, elongated voids, not near-perfect spheres. The Boötes Void, by contrast, appeared almost geometrically pure, as if carved with intention. There were attempts to explain it away. Perhaps it was an observational artifact, a trick of redshift surveys that had missed galaxies lurking in the shadows. Follow-up studies, however, confirmed the void's reality. Deep imaging revealed that the region was not completely empty. There were a few dozen dwarf galaxies scattered throughout, but their presence only deepened the mystery. Why would small galaxies form here, but not large ones? What prevented the normal processes of galaxy assembly from taking hold in this region? And if the void was real, what did that mean for our understanding of cosmic evolution? The problem is not simply that the void exists. The problem is that its existence implies a level of inhomogeneity in the early universe that we have not accounted for. When we measure the cosmic microwave background, the radiation left over from the moment the universe became transparent. Roughly 380,000 years after the Big Bang, we see a nearly uniform glow. The temperature variations across the sky are minuscule, on the order of 1 part in 100,000. These tiny fluctuations are the seeds of all cosmic structure. Over billions of years, regions that were slightly denser than average pulled in more matter through gravity, eventually forming galaxies and clusters. Regions that were slightly less dense became voids. But the Boötes Void is not slight. It is a deviation so extreme that it challenges the assumption of smoothness embedded in our cosmological models. If such a void could form from the initial conditions we observe in the microwave background, then either our understanding of structure formation is incomplete, or the early universe was not as uniform as we believe. Both possibilities are unsettling. There is also the question of what the void tells us about dark matter. The current model of cosmology lambda cold dark matter, RCD-M, predicts that dark matter, which makes up roughly 85% of all matter in the universe, formed the scaffolding upon which galaxies assembled. Ordinary matter fell into the gravitational wells created by dark matter, condensing into stars and galaxies. If this model is correct, then the Boötes Void should also contain dark matter, just in lower concentrations. But if dark matter is present, why did it not pull in enough ordinary matter to form galaxies? And if dark matter is absent, where did it go? Dark matter cannot simply evaporate. It does not interact with radiation or ordinary matter in ways that would allow it to be expelled from a region. Its presence is dictated entirely by gravity, and gravity does not forget. The void forces us to ask whether the universe, on its largest scales, is truly governed by the principles we have assumed. Is the cosmological principle a law, or merely an approximation that holds most of the time? And if it is only an approximation, what does that mean for the predictions we have made about the universe's past and future? The discomfort scientists felt upon discovering the Boötes Void was not rooted in fear of the unknown, but in something more fundamental, the recognition that a cornerstone of cosmology might be less stable than believed. For decades, the universe had been described as a place of statistical fairness. Yes, there were clusters and filaments, peaks and valleys in the distribution of matter. But these were understood to be natural consequences of gravitational amplification acting on tiny primordial fluctuations. The void suggested something else, that perhaps the universe's initial conditions were not as uniform as the cosmic microwave background implied, or that the processes governing structure formation were more complex, more capable of extremes than our models allowed. What made the void particularly troubling was its timing. By the early 1980s, cosmology had just emerged from a period of profound uncertainty. The discovery of the microwave background in 1965 had confirmed the Big Bang model, but questions remained about how structure formed. Galaxies, clusters, and superclusters existed, but the mechanism by which they arose from an almost perfectly smooth early universe was not yet clear. The introduction of dark matter into cosmological models helped resolve some of these issues, providing the invisible gravitational scaffolding needed to explain why galaxies clustered the way they did. The Boötes Void, however, arrived just as this framework was being solidified, and it introduced a wrinkle that could not be easily smoothed over. One immediate question was whether the void represented a failure of observation or a failure of theory. Early redshift surveys were limited in scope and depth. They captured only the brightest galaxies, those visible across vast distances. It was conceivable that dimmer galaxies filled the void, invisible to the surveys of the time. Subsequent observations, using more sensitive instruments, confirmed that while the void was not absolutely empty, it was still remarkably underpopulated. The few galaxies that did exist within it were predominantly small. Low-luminosity systems dwarf galaxies that seemed almost accidental, as if they had formed despite the void rather than because of it. This partial occupancy posed its own puzzle. If conditions in the void were hostile to galaxy formation, why did any galaxies form at all? And if conditions were not hostile, why were there so few? Galaxy formation is not a binary process. It is a continuum, driven by the availability of gas, the strength of gravitational wells, and the feedback mechanisms that regulate star formation. In a typical region of space, these factors produce a wide range of galaxy-type spirals, ellipticals, irregulars each, representing a different balance of forces. In the Boötes Void, however, this diversity was absent. The galaxies that existed were almost uniformly small and faint, suggesting that something about the environment suppressed the formation of larger systems. One possibility is that the void began as a region of slightly lower density in the early universe, and that this initial deficit was amplified over time. As matter in surrounding regions began to collapse under gravity, forming protogalaxies and clusters, the void became increasingly isolated. Gas and dark matter flowed outward, drawn toward the denser regions nearby, leaving the void progressively emptier. This is a known mechanism in cosmology. Voids grow through a process called gravitational evacuation, in which matter migrates from underdense regions to overdense ones. But even accounting for this process, the Boötes Void is unusually empty. Standard models predict that voids should retain a certain baseline density, enough to support the formation of at least some galaxies. The Boötes Void falls below this baseline, suggesting that something more than simple gravitational evacuation is at play. Another hypothesis involves the role of dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, is thought to be uniformly distributed across space. But what if it is not? What if there are regions where dark energy is slightly more dominant, creating a repulsive effect that counteracts gravity more strongly than elsewhere? In such regions, matter would be pushed outward more aggressively, preventing the collapse necessary for galaxy formation. This idea remains speculative. There is no direct evidence that dark energy varies from place to place, but the Boötes Void provides a tantalizing hint that our assumptions about its uniformity may need revisiting. There is also the question of what the void implies about the cosmic web itself. The large-scale structure of the universe is often described as a network of filaments and walls, with galaxies concentrated along these features and voids occupying the spaces in between. This structure is thought to arise naturally from the way gravity amplifies density fluctuations over time. But the Boötes Void is not simply a gap in the web. It is too large, too well defined. It resembles not a passive absence, but an active exclusion, a bubble carved into the fabric of the cosmos. Some researchers have speculated that the void might be the remnant of a primordial bubble, a region where the physics of the early universe played out differently, leaving behind a permanent scar. This brings us to the deeper question: is the void a problem of absence or a problem of presence? Are we looking at a region where something failed to happen, or a region where something unusual did happen? The distinction matters. If the void is simply an extreme statistical fluctuation, rare but not impossible, outcome of the processes we already understand, then it is unsettling but not paradigm-breaking. We would need to adjust our models slightly, recalibrate our expectations, but the fundamental framework would remain intact. If, however, the void is evidence of a process we have not accounted for, a new force, a different kind of matter, a deviation from the cosmological principle that cannot be explained by known physics, then the implications are far more profound. What the Boötes Void demands is not an answer, but a reckoning. It asks us to confront the possibility that the universe, for all its apparent regularity, is capable of surprises that challenge the very assumptions upon which our understanding rests. It is a reminder that cosmology, despite its mathematical elegance and observational precision, still a work in progress, built on models that approximate reality but do not fully capture it. The void is not merely an empty space. It is a question written in the architecture of the cosmos, a challenge to the notion that we have fully grasped the rules by which the universe organizes itself. And it is only the first of many such questions. The Boötes Void is the largest and most famous, but it is not alone. Other supervoids have been discovered since, each raising similar issues, each suggesting that the universe's structure is more irregular, more unpredictable than we would like to believe. Together, they form a constellation of absences, each one a reminder that the cosmos does not always conform to our expectations. The problem of absence, it turns out, is not just about what is missing. It is about what that absence reveals about the limits of our knowledge, the fragility of our assumptions, and the enduring mystery of a universe that refuses to be fully known. The human eye is an instrument of survival, not truth. It evolved over millions of years to perform a single task with ruthless efficiency, to detect objects that matter: a predator in the underbrush, a fruit hanging from a branch, a crack in the stone that might be shaped into a blade. Our ancestors did not need to perceive the space between things. They needed to identify the things themselves, to distinguish figure from ground, signal from noise. The brain, working in concert with the eye, learned to filter reality accordingly. It highlights edges, contrasts, and movement. It assigns meaning to shape and color. And it dismisses the rest, the backdrop, the intervals, the emptiness, as irrelevant. This is not a flaw. It is a triumph of evolutionary engineering. A mind that pays equal attention to everything would be paralyzed by information. The savanna does not reward contemplation of negative space. It rewards focus, speed, and the ability to make decisions based on what is present, not what is absent. And so we became creatures of presence, attuned to matter, conditioned to see the world as a collection of objects separated by voids that do not themselves require attention. This bias persists, encoded in the deepest layers of perception. Even now, when we look at the night sky, we do not see the darkness. We see the stars. The vast stretches of black between them register as mere background, a canvas upon which the real universe is painted. We map constellations, trace the paths of planets, and catalog galaxies, all the while treating the emptiness as secondary, a passive stage on which matter performs. It is only when the absence becomes extreme, when the void grows large enough to demand acknowledgement, that we are forced to reckon with what we have been ignoring all along. The Boötes Void is such an absence. It is too large, too empty to dismiss as background. And yet, even when confronted with it, our instinct is to focus on what little matter it contains. We ask why there are few galaxies rather than asking what the emptiness itself represents. We treat the void as a failure of structure, a gap in the cosmic web, rather than considering the possibility that the void is structure. This cognitive reflex to privileged presence over absence runs so deep that it shapes not only how we observe the universe, but how we theorize about it. For most of human history, the concept of empty space was philosophically troubling. The ancient Greeks debated whether a true vacuum could exist. Aristotle argued that nature abhors a vacuum, that the universe must be filled with substance, even if that substance is invisible. This idea persisted for centuries, influencing medieval and Renaissance thought. The notion that space could be truly empty, containing neither matter nor medium, was seen as a kind of metaphysical impossibility. Even after the scientific revolution, when the existence of a vacuum became experimentally verifiable, the discomfort lingered. Space was not supposed to be nothing. It was supposed to be something ether fields, quantum foam anything but absolute emptiness. This discomfort, sometimes called horror vacui, is not merely historical. It persists in subtle ways within modern cosmology. We describe the universe in terms of matter and energy, mapping the distribution of galaxies and dark matter halos, constructing models of structure formation that trace how overdense regions evolve over time. Voids, by contrast, are defined negatively. They are the regions where galaxies are not. They are the leftovers, the spaces evacuated by gravitational dynamics, the background against which the real action unfolds. We study them, yes, but always in relation to what surrounds them, rarely as entities in their own right. Yet the Boötes Void suggests that this perspective may be backwards. What if the emptiness is not a byproduct of structure, but a primary feature? What if voids are not simply the absence of matter, but something more fundamental, regions where the conditions for galaxy formation were not merely suppressed but inverted? The universe, after all, is not obligated to conform to our intuitions about what should exist and where. If we are to understand its true architecture, we must learn to see what is not there, to assign meaning to the spaces between the light. This requires a shift in perception that does not come naturally. Our brains are not wired to think in terms of absence. When we encounter a gap, we instinctively try to fill it, to explain it away, to reduce it to something more familiar. A void is uncomfortable because it resists this impulse. It cannot be filled with narrative or extrapolation. It simply is a region where the expected rules do not apply, where the presence we anticipate fails to materialize. And because we cannot fill it, we are left with the unsettling realization that the universe contains more nothing than we ever imagined. The difficulty is compounded by the limitations of astronomical observation. We study the cosmos by collecting light. Telescopes, regardless of their power, are instruments designed to detect photons, particles emitted or reflected by matter. A galaxy shines because it contains stars. A nebula glows because its gas is ionized. Even dark matter, which does not emit light, reveals itself through gravitational lensing, a bending of the light of more distant objects. Everything we know about the universe comes from light, and light requires a source. The void, by definition, has no sources. It is a region where light does not originate, where galaxies do not form, where the usual tracers of cosmic structure are absent. To study it, we must rely on what surrounds it, inferring its properties from the edges, from the negative space defined by the presence of matter elsewhere. This method works, but it is indirect. It is like trying to understand a sculpture by examining only the clay that was removed, never touching the form that remains. We can deduce the void's size, its shape, its relative emptiness, but we cannot observe it directly. We cannot send probes into it, cannot sample its contents, cannot measure its properties in the way we measure the properties of a star or a planet. The void exists as a shadow, a gap in our data, a region where our instruments fall silent. And because we cannot see it, we struggle to integrate it into our understanding of the cosmos. It remains, in some fundamental sense, invisible. This invisibility is not merely a technical problem, 'tis a conceptual one. The void challenges the way we construct knowledge about the universe. Science, at its core, is an empirical discipline. We observe, we measure, we test hypotheses against data. But the void gives us very little data. It is defined by what is missing, and absence is difficult to quantify. How do you measure the properties of nothing? How do you test theories about a region where the expected phenomena do not occur? The void does not fit neatly into the frameworks we have developed for studying the cosmos, and so it exists at the periphery of cosmological discourse. Knowledge, knowledge, but not fully integrated, understood in outline, but not in detail. The psychology of perception extends beyond the individual observer. It shapes entire fields of inquiry, determining not only what we study, but how we study it. Astronomy, for most of its history, has been a discipline of cataloging light. We name stars, classify galaxies, measure distances to quasars. We build ever larger telescopes to capture fainter signals, pushing the boundaries of visibility outward. The implicit assumption is that the universe reveals itself through luminosity. That understanding comes from collecting more photons, from seeing further and with greater clarity. The void, however, cannot be understood this way. It does not become clearer when we build better telescopes. It remains stubbornly empty, offering no new sources to catalog, no additional signals to decode. The tools we have developed to study the cosmos are optimized for presence, not absence, and the void reminds us that these tools have limits. This limitation is not unique to astronomy. It reflects a broader human tendency to organize knowledge around positive categories. We classify animals by what they are, not by what they are not. We define diseases by their symptoms, not by their absence. We map territories by marking borders, not by charting the unmarked spaces in between. Absence is difficult to categorize because it lacks the discrete features that make classification possible. A void is not a type of galaxy. It is not a structure in the conventional sense. It is a negation, and negation resists the taxonomies we impose on the natural world. Yet negation can be informative. In mathematics, zero is not merely the absence of quantity. It is a number with its own properties, essential to the structure of arithmetic. In physics, a vacuum is not simply empty space. It seethes with quantum fluctuations, virtual particles flickering in and out of existence. Contributing to phenomena like the Casimir effect and Hawking radiation, absence, when examined closely, often reveals itself to be a kind of presensus state with its own dynamics, its own rules, its own consequences. The question is whether the Boötes void, and voids like it, possess similar hidden properties. Are they merely regions where matter failed to accumulate? Or do they represent a distinct state of cosmic structure, one that requires its own theoretical framework? Some cosmologists have begun to approach the void this way, not as a gap to be explained away, but as a phenomenon to be studied in its own right. They ask what physical processes might create such a region, what conditions would prevent galaxy formation on such a scale, and whether voids might influence the evolution of the universe in ways we have not yet considered. These questions are difficult because they require inverting the usual logic of cosmology. Instead of asking how matter clumps together, we must ask how it stays apart. Instead of modeling the growth of structure, we must model its absence. This shift in perspective is subtle, but it has profound implications. It suggests that the universe's architecture is not fully described by the distribution of galaxies alone, but by the interplay between regions of high density and regions of low density, between the places where matter congregates and the places where it does not. This interplay is visible in the cosmic web, the large-scale structure that emerges when we map the distribution of galaxies across the observable universe. The web consists of filaments, walls, nodes regions, where galaxies cluster and voids, the vast empty regions in between. The pattern resembles a foam, with bubbles of emptiness separated by thin membranes of matter. The voids occupy most of the volume of the universe, yet they contain very little mass. The filaments and walls, by contrast, occupy a small fraction of the volume, but contain most of the galaxies. This is a universe defined as much by absence as by presence. A cosmos in which the empty spaces are not incidental, but integral to the overall structure. The Boötes Void, however, does not fit comfortably within this picture. It is too large to be a typical void, too spherical to be a natural consequence of gravitational dynamics. It suggests that the cosmic web is not as regular as we might hope, that the processes shaping the universe's structure are capable of producing anomalies that challenge our models. And it raises the possibility that our focus on galaxies and clusters has caused us to overlook something important about the voids themselves, that they are not simply empty, but differently structured, governed by dynamics we have not yet fully understood. One way to think about this is to consider what the universe would look like from within the void. An observer stationed in the Boötes Void would experience a cosmos radically different from our own. The night sky would be almost featureless, with only a handful of faint galaxies visible even with powerful telescopes. The cosmic microwave background, the faint glow of the Big Bang, would still be present. But there would be no nearby galaxies to study. No local group to anchor cosmological models, no direct evidence that the universe beyond the void is populated and structured. Such an observer would have a profoundly different understanding of reality. They might conclude that the universe is far emptier than it actually is, that galaxies are rare and isolated, that the cosmos is dominated by emptiness rather than matter, and they would not be entirely wrong. From their perspective, that is the universe they inhabit. This thought experiment reveals something essential about the nature of cosmological knowledge. Our understanding of the universe is conditioned by our location within it. We live in a region where galaxies are common, where structure is evident, where the cosmic web is visible in all directions. We assume this is representative, that the universe looks roughly the same everywhere, but the Boötes Void suggests otherwise. It suggests that there are regions where the universe is fundamentally different, where the usual patterns do not hold, where an intelligent observer would develop a cosmology unlike our own. And if this is true, then our models may be more parochial than we realize, optimized for the kind of universe we happen to inhabit. Less applicable to regions where the rules are different. The void also forces us to reconsider what we mean by structure. In physics, structure typically implies order, organization, the presence of patterns that can be described mathematically. A crystal has structure. A galaxy has structure. But does a void have structure? At first glance, the answer seems to be no. A void is defined by the absence of galaxies, by the lack of organization, by the uniformity of emptiness. But uniformity itself is a kind of structure. A perfectly empty region is not random. It is highly ordered, in the sense that it deviates from the expected distribution of matter in a consistent, non-arbitrary way. The Boötes Void is not a chaotic jumble of empty space. It is a geometrically coherent region, spherical in shape, with well-defined boundaries. This coherence suggests that something structured its formation, that the void is not merely the absence of galaxies, but the result of processes that imposed a particular configuration on the cosmos. What those processes might be remains uncertain. They could be gravitational, the result of matter flowing away from an initially underdense region, leaving behind a cavity that expanded over time. They could be related to dark energy, the mysterious force driving the universe's accelerated expansion, creating regions where repulsion dominates over attraction. They could even be primordial, remnants of the universe's earliest moments, when quantum fluctuations imprinted patterns on space itself. Each of these possibilities has implications for how we understand the cosmos. And each requires us to think about voids not as passive gaps, but as active participants in the universe's evolution. The limitation of the visual, then, is not simply that we cannot see the void. It is that our entire framework for understanding the universe is built on what we can see, and the void exists outside that framework. It is a reminder that light, for all its utility, is not the only way the universe communicates its structure. Darkness, too, carries information. Absence, too, tells a story. And if we are to understand the cosmos in its entirety, we must learn to read both. The light and the shadow, the matter and the void, the presence and the absence that together define the architecture of everything that exists. Gravity does not create, it gathers. It does not impose order from above, but emerges from below. From the accumulated influence of mass-bending space, drawing matter toward matter in an endless patient collapse. This is the engine of cosmic structure, the force that transforms the near-uniform distribution of the early universe into the intricate architecture we observe today. And yet, gravity alone is not enough. Without something to amplify its effects, without invisible scaffolding to anchor the process, the universe would have remained far more homogeneous than it is. The galaxies, the clusters, the vast filaments stretching across hundreds of millions of light-years, of this required a foundation that ordinary matter could not provide. That foundation is dark matter. It does not emit light, does not interact with electromagnetic radiation, and cannot be detected directly by any instrument we have built. Its existence is inferred entirely through its gravitational effects, the way galaxies rotate, the way clusters hold together, the way light bends around massive objects that we cannot see. Dark matter is thought to comprise roughly 85% of all matter in the universe, yet it remains invisible, perceptible only through the influence it exerts on the small fraction of matter that we can observe. It is this dark matter that formed first, collapsing under its own gravity into dense halos long before the first stars ignited. Ordinary matter, the hydrogen and helium forged in the first moments after the Big Bang fell into these halos, cooling and condensing into the galaxies we see today. The result is the cosmic web, the largest known structure in the universe. It is not a random scattering of galaxies, but an organized network. A three-dimensional lattice of filaments and walls with vast voids in between. The filaments are rivers of galaxies flowing along invisible currents of dark matter. The walls are thin sheets where galaxies cluster, marking the boundaries between empty regions. And the voids are the spaces left over, the bubbles in the foam. The regions where matter did not accumulate because there was no gravitational anchor to hold it in place. This structure did not emerge overnight. It is the product of nearly 14 billion years of gravitational evolution. A slow transformation of the universe from smooth to clumpy, from simple to complex. The process began in the earliest moments when quantum fluctuations during the inflationary epoch imprinted tiny variations in the density of matter across space. These fluctuations were minuscule differences of only 1 part in 100,000, but they were enough. In regions that were slightly denser than average, gravity pulled in more matter, making them denser still. In regions that were slightly less dense, matter drifted away, leaving them emptier. Over time, this feedback loop amplified the initial fluctuations, transforming imperceptible variations into the dramatic structures we observe today. The evidence for this process is written in the cosmic microwave background. The afterglow of the Big Bang. When we map the temperature of this radiation across the sky, we see a pattern of hot and cold spots, regions where the density of matter was slightly higher or lower when the universe was just 380,000 years old. These spots correspond to the seeds of galaxies and voids. The hot spots mark regions where matter would eventually collapse into filaments and clusters. The cold spots mark regions that would become voids. The pattern is not random. It has a characteristic scale, a typical size for the fluctuations determined by the physics of the early universe. This scale sets the size of the structures that form later, dictating how large voids can grow and how tightly galaxies cluster. According to the standard model of cosmology, lambda cold dark matter, the growth of structure follows predictable rules. Dark matter collapses first, forming halos that serve as gravitational wells. Ordinary matter falls into these wells, cooling and condensing into stars and galaxies. As galaxies form along filaments, the regions between the filaments, the voids, expand. This expansion is not driven by any repulsive force, but by the simple fact that matter is flowing away, pulled by gravity toward the denser regions nearby. The voids grow passively, evacuated by the same process that builds the cosmic web. They are not active participants in the story of structure formation, but byproducts, the negative space left behind as matter organizes itself into galaxies. This framework has been remarkably successful. It explains the large-scale distribution of galaxies, the clustering patterns we observe in surveys, the statistical properties of the cosmic web. It predicts that voids should be common, that they should occupy most of the volume of the universe, and that they should have a characteristic size determined by the spacing of filaments in the web. Observations confirm these predictions. When we map the positions of millions of galaxies, we see exactly the kind of structure the model describes: a network of filaments surrounding voids, with galaxies concentrated along the filaments and sparse within the voids. But the model also makes predictions about the limits of structure. It tells us how large voids can grow, how empty they can become, and how their properties should vary with the age of the universe. These predictions are not arbitrary. They are consequences of the laws of gravity and the initial conditions imprinted in the cosmic microwave background. If the model is correct, then the universe's structure is not infinitely variable. There are constraints, boundaries, beyond which certain configurations should not occur. The cosmic web, for all its complexity, is not chaotic. It is ordered, governed by rules that emerge from the interplay of gravity, dark matter, and the expansion of space. The Boötes Void, however, appears to violate these constraints. It is larger than the model predicts, emptier than the average void should be, and more spherical than the typical bubble-like voids formed by gravitational evacuation. Its size alone is troubling. The standard model allows for voids of a certain scale, determined by the distance between filaments in the cosmic web. Most voids fall within this range, with diameters of tens to perhaps 100 million light-years. The Boötes Void is more than 3 times larger, stretching across 330 million light-years. This is not a modest deviation. It is an outlier, a structure that sits at the extreme edge of what the model permits, if not beyond it. The emptiness of the void is equally puzzling. Voids are not supposed to be completely empty. They should contain some galaxies, particularly small dwarf galaxies that form in the lower density regions. The Boötes Void does contain a few such galaxies, but far fewer than expected. The density of matter within it is only about 10% of the average density of the universe, a deficit that is difficult to explain through gravitational evacuation alone. If matter flowed out of the void as the model suggests, where did it go? The surrounding regions are not correspondingly overdense. There is no obvious accumulation of galaxies at the void's edges, no sign of the matter that should have been displaced. The void appears to have lost mass without a clear destination, as if it were drained by a process the standard model does not account for. The shape of the void is perhaps the most telling detail. Gravitational evacuation, the process by which matter flows from underdense regions toward overdense ones, does not produce perfect spheres. It produces irregular, elongated voids, shaped by the distribution of filaments around them. The cosmic web is not uniform. Filaments run in different directions with varying densities and separations, and the voids that form between them reflect this irregularity. They are stretched, compressed, and distorted by the gravitational landscape in which they sit. The Boötes Void, by contrast, is remarkably spherical. Its boundaries are smooth, its geometry almost ideal. This symmetry suggests that the void did not form through the chaotic directional process of gravitational flow, but through something more uniform, something that acted equally in all directions. One possibility is that the void represents an extreme statistical fluctuation, a rare but not impossible outcome of the initial conditions in the early universe. In any large enough volume of space, there will be regions where the density fluctuations happen to be larger or smaller than average. The cosmic microwave background shows us the average scale of these fluctuations, but it does not preclude the existence of outliers. If the Boötes Void began as a region with an unusually low initial density, then its subsequent evolution could have amplified this deficit, producing a void larger and emptier than the typical case. This explanation has the advantage of requiring no new physics. It fits within the framework of lambda-cold dark matter, attributing the void's properties to chance rather than to any fundamental deviation from the standard model. But statistical arguments have limits. The probability of a fluctuation depends on how extreme it is. Small deviations from the average are common. Large deviations are rare. Extremely large deviations are so improbable that their existence demands explanation. The Boötes Void, if it is merely a statistical outlier, is at the very edge of what the model permits. Some calculations suggest that voids of this size should occur only once or twice in the entire observable universe. The fact that we observe it at all is surprising, but not impossible. The fact that other large voids have since been discovered, however, begins to strain this explanation. If such voids are common enough to be found in multiple surveys, then perhaps they are not outliers at all, but signatures of a process that the standard model has not fully captured. Another possibility involves the role of dark energy. Dark energy is the term used to describe the force driving the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy pushes space apart, causing galaxies to recede from one another at an ever-increasing rate. This force is thought to be uniform, present everywhere in equal measure. But its effects become noticeable only on the largest scales and over the longest timescales. In the early universe, when matter was denser and gravity dominated, dark energy had little influence. As the universe expanded and matter became more dilute, dark energy gradually took over, eventually becoming the dominant force shaping the cosmos. If dark energy is not perfectly uniform, if it varies slightly from place to place, then it could influence the growth of voids in ways the standard model does not account for. In regions where dark energy is slightly stronger, the repulsive effect would be more pronounced, accelerating the expansion of voids and preventing matter from falling back in. This would produce voids that are larger and emptier than expected. Exactly what we observe in the Boötes Void. The problem with this idea is that there is no direct evidence that dark energy varies. It is assumed to be a property of space itself, a cosmological constant with the same value everywhere. But assumptions can be tested, and the existence of supervoids like Boötes provides a reason to test this one. There is also the question of what the cosmic web itself reveals about the underlying physics. The web is not static. It evolves over time, responding to the changing balance between gravity and dark energy. In the early universe, gravity dominated and structure grew rapidly. Dark matter halos formed, galaxies assembled, and filaments stretched across the cosmos. As dark energy became more influential, this growth slowed. The expansion of space began to compete with the collapse of matter, and the largest structures, the superclusters and supervoids, became frozen in place, unable to evolve further. The cosmic web we observe today is a snapshot of this process, a record of how structure formation unfolded over billions of years. The Boötes Void, however, does not fit neatly into this timeline. If it formed through the same processes that shape the rest of the cosmic web, it should have begun as a small underdensity and grown gradually over time. but its size suggests that it has been growing for longer or more rapidly than the standard model predicts. One way to reconcile this is to assume that the void began with an unusually large initial underdensity, larger than the typical fluctuations seen in the cosmic microwave background. This would give it a head start, allowing it to grow to its current size within the age of the universe. But this explanation requires that the early universe was less uniform than we thought, that the fluctuations in density were more variable, more capable of producing extremes than the simple statistical models suggest. Alternatively, the void could have grown more rapidly because the physics of its formation is different. Something other than gravity and dark energy influenced its evolution. Some additional force or process that we have not yet identified than the void's growth could have been accelerated beyond what the standard model allows. This is speculative, but it is not without precedent. The history of cosmology is filled with moments when observations forced physicists to add new components to their models. Dark matter itself was once a speculative idea introduced to explain the rotation curves of galaxies. Dark energy was discovered only in the late 1990s, when observations of distant supernova revealed that the universe's expansion is accelerating. Both of these discoveries required revisions to the standard model, the addition of new phenomena that were not initially anticipated. The Boötes Void may be signaling the need for another such revision. What makes this possibility compelling is not just the size or emptiness of the void, but the coherence of its structure. A void formed through random gravitational dynamics should show signs of that randomness: irregular boundaries, asymmetries, variations in density across its interior. The Boötes Void, however, is smooth, spherical, and remarkably uniform. Its coherence suggests that it was shaped by a process that acted globally, not locally. A process that imposed order on a scale larger than the typical interactions between filaments and voids. This is not the signature of chaos amplified by gravity. It is the signature of something more organized, more systematic. Something that left an imprint we have not yet learned to read. The architecture of nothing, then, is not as simple as the standard model suggests. Voids are not merely passive gaps in the cosmic web, evacuated by the flow of matter toward denser regions. They are active components of the universe's structure, shaped by forces that may extend beyond gravity and dark energy, influenced by initial conditions that may have been more complex than the smooth fluctuations we see in the cosmic microwave background. The Boötes Void is a reminder that the rules of cosmic construction are still being written, that the universe is capable of producing structures that challenge our assumptions and push the boundaries of our models. And it suggests that if we are to understand the full architecture of the cosmos, we must learn to see the voids, not as absences, but as presences in their own right regions, where the hidden influences shaping the universe reveal themselves most clearly. A telescope does not see emptiness, collects photons, counts them, measures their wavelengths, and constructs from this data an image of the universe. But photons must come from somewhere. They are emitted by stars, reflected by dust, scattered by gas. Without a source, there is nothing to detect, nothing to measure, nothing to map. And so the astronomer faces a paradox. How do you study a region defined by the absence of the very thing your instruments are built to find? The answer lies not in looking at the void itself, but in tracing its boundaries. If the void contains almost no galaxies, then mapping it becomes a matter of establishing where galaxies are not. This requires surveying the surrounding regions with enough precision to define the edges, to measure the transition from populated space to empty space, and to infer from this transition the shape and extent of the absence within. It is cartography through negation, a method that relies on marking the coastline in order to map the ocean. The primary tool for this work is the redshift survey. Redshift is a measure of how much the wavelength of light has been stretched as the universe expands. A galaxy moving away from us emits light that appears shifted toward the red end of the spectrum. And the degree of this shift tells us how far away the galaxy is. By measuring the redshifts of thousands of galaxies, astronomers can construct a three-dimensional map of cosmic structure, plotting not just where galaxies appear on the sky, but how far away they are in space. This transforms the flat, two-dimensional view of the night sky into a volume, revealing the depth and architecture of the universe. The first redshift surveys were laborious. Each galaxy had to be observed individually, its light captured by a spectrograph and analyzed to determine its redshift. This was slow work, requiring hours of telescope time for each object. By the early 1980s, when Robert Kirshner and his colleagues began their survey of the Boötes region, the technology had improved, but the process remained painstaking. They selected a narrow strip of sky, a pencil beam pointing into the constellation Boötes, and measured the redshifts of every galaxy they could find within it. The goal was not to map the entire sky, but to probe deeply into one direction, sampling the distribution of galaxies along a single line of sight. What they found was unexpected. For millions of light-years, the survey detected galaxies at regular intervals, clustered along filaments as expected. Then, abruptly, the signal stopped. For a vast stretch of distance, corresponding to a region more than 300 million light-years across, there were almost no galaxies. The redshift survey had pierced through a void, and the absence of data was itself the discovery. The void revealed itself not through what the telescope saw, but through what it did not see. This method of detection carries inherent uncertainties. A single pencil beam survey samples only a narrow slice of space. It cannot determine whether the void is spherical, elongated, or irregular without additional observations from different directions. It cannot tell whether the absence of galaxies is uniform throughout the void, or whether there are hidden pockets of structure that the survey missed. And it cannot confirm that the void is truly empty, only that it contains fewer bright galaxies than expected. Faint galaxies, too dim to be detected by the survey's sensitivity limits, could still be present in large numbers, hidden in the noise. To address these limitations, subsequent surveys targeted the same region with greater sensitivity and broader coverage. They used larger telescopes, longer exposure times, and more advanced detectors, searching for the faint signatures of dwarf galaxies and gas clouds that might have escaped earlier detection. These follow-up studies confirmed the void's existence and refined its properties. They found that while the void was not completely empty, it was profoundly underpopulated. The few galaxies it contained were small, low-luminosity systems, the kind that form in isolation rather than within the dense environments of galactic clusters. The void was real, and it was vast. But knowing that the void exists is not the same as understanding what it contains. Galaxies are not the only form of matter in the universe. There is also intergalactic gas, clouds of hydrogen and helium that fill the space between galaxies, invisible to most telescopes because they do not emit light on their own. This gas can be detected indirectly through absorption lines in the spectra of distant quasars. A quasar is an extremely bright, distant object powered by a supermassive black hole. Its light travels across billions of light-years before reaching us, passing through whatever gas lies along the way. If that gas is present, it absorbs specific wavelengths of light, leaving dark lines in the quasar spectrum. By analyzing these absorption lines, astronomers can map the distribution of intergalactic gas, even in regions where no galaxies are visible. This technique, known as quasar absorption spectroscopy, has been used to probe the Boötes Void. Astronomers identified quasars located behind the void, their light passing through the empty region on its way to Earth. If the void contained significant amounts of intergalactic gas, that gas would leave its fingerprint in the quasar spectra. The results were ambiguous. Some absorption lines were detected, indicating that the void is not a perfect vacuum, but the amount of gas appeared to be lower than expected. The void was underdense, not just in galaxies, but in the raw material from which galaxies form. This raised a deeper question. If the void contains less gas than surrounding regions, where did that gas go? Gas cannot simply disappear. It must either remain in place to diffuse to form stars, or it must have been expelled, pushed out of the void by some process that has yet to be identified. In typical voids, gas is thought to flow along filaments, drawn by gravity toward overdense regions where it eventually collapses into galaxies. But the Boötes Void is too large for this explanation to fully account for its emptiness. The gas would have had to travel hundreds of millions of light-years to reach the surrounding filaments, a journey that would take billions of years. The age of the universe places constraints on how far gas can travel, and the Boötes Void pushes up against those constraints. Another approach to measuring the void involves gravitational lensing. Gravitational lensing occurs when the mass of an object bends the path of light passing near it, distorting the images of more distant objects. This effect can be used to map the distribution of mass, including dark matter, which does not emit light but still exerts gravitational influence. If the Boötes Void is truly empty, then light passing through it should experience less lensing than light passing through a typical region of space. By comparing the distortion of background galaxies seen through the void to the distortion seen through other regions, astronomers can estimate the mass deficit within the void and confirm whether it is as empty as the galaxy count suggests. These lensing studies are challenging because the effect is subtle. The void's influence on light is weak, and detecting it requires precise measurements of the shapes and positions of thousands of background galaxies. The signal must be extracted from noise, corrected for instrumental effects, and compared to theoretical predictions that depend on assumptions about the distribution of dark matter and the geometry of space. The uncertainties are large and the conclusions are provisional, but the results so far are consistent with the void being genuinely underdense in both ordinary and dark matter. The silence, it seems, extends beyond the visible. It is a silence of mass itself. The fragility of this knowledge cannot be overstated. The map of the Boötes Void is not a photograph. It is a reconstruction assembled from disparate observations, each with its own limitations and uncertainties. Redshift surveys tell us where galaxies are, but not where gas or dark matter might be hiding. Quasar absorption spectra tell us about the gas along a few narrow sightlines, but not about the structure of the void as a whole. Gravitational lensing tells us about the total mass, but cannot distinguish between different forms of matter or reveal their detailed distribution. Each method samples a different aspect of reality, and the full picture emerges only when these fragments are combined, interpolated, and interpreted through the lens of theory. This process of reconstruction is common in astronomy, but it takes on a particular poignancy when applied to voids. In most cases, astronomers are trying to detect something: a star, a planet, a galaxy, and the challenge is to extract a faint signal from the background. With voids, the challenge is reversed. The goal is to confirm the absence of a signal, to prove that the lack of detection is not merely a failure of observation, but a genuine feature of the universe. This requires ruling out alternative explanations: that the galaxies are there but too faint to see, that the gas is present but not detectable with current instruments, that the void is an artifact of incomplete data or biased sampling. Each of these alternatives must be tested and rejected, one by one, before the void can be confidently mapped. This is slow, meticulous work requiring observations at multiple wavelengths with different instruments over many years. It is work that does not yield dramatic images or striking visual evidence. The data is often mundane tables of redshifts, lists of absorption lines, statistical analyses of lensing signals. The void itself remains invisible, perceptible only through the patterns of absence that emerge from these numbers. Yet this invisibility is precisely what makes the void scientifically compelling. In most of astronomy, the challenge is to see further, to detect fainter objects, to push the limits of observation outward. With voids, the challenge is different. It is to construct knowledge from the lack of data, to infer structure from emptiness, to understand what is not there as fully as what is. This requires a different kind of rigor, a careful attention to what has not been observed and why, and a willingness to accept that some features of the universe are defined by absence rather than presence. The tools used to study voids have evolved considerably since the 1980s. Modern redshift surveys observe millions of galaxies, not thousands, mapping vast volumes of space with unprecedented completeness. Automated telescopes and fiber optic spectrographs can measure hundreds of redshifts simultaneously, accelerating the pace of discovery. Deep imaging surveys probe fainter objects, revealing dwarf galaxies and low-surface brightness structures that earlier surveys missed. Quasar catalogs have expanded, providing more sightlines through the void, more opportunities to sample the intergalactic gas. Gravitational lensing surveys cover larger areas of sky, improving the statistical power of mass measurements. All of these advances have refined our understanding of the Boötes Void, but they have not resolved the central mystery. The void remains larger, emptier, and more spherical than the standard models predict. Its boundaries are sharper than expected, its interior more uniform. And while the void is no longer unique, other supervoids have been discovered. Some even larger, the questions it raises have not been answered. Each new void adds to the puzzle, suggesting that these structures are not rare anomalies but recurring features of the cosmic landscape, signatures of processes that our models have not yet fully captured. One of the most intriguing aspects of measuring the void is the role of time. The universe is not static. It is expanding, evolving, changing its structure as gravity pulls matter together and dark energy pushes space apart. The void we observe today is not the void that existed 1 billion years ago. Nor is it the void that will exist 1 billion years from now. It is a snapshot, a momentary configuration of a system in flux. To understand the void fully, we must understand not just where it is and what it contains, but how it came to be and where it is going. This requires simulations, computational models that evolve the universe forward from its initial conditions, tracking the motions of billions of particles over billions of years. These simulations are built on the laws of gravity and the properties of dark matter and dark energy, and they predict how structure should form and evolve over time. By comparing the simulations to observations, astronomers can test whether the models are correct, whether they capture the full complexity of cosmic evolution. The Boötes Void, in this context, becomes a test case, a benchmark against which the simulations must be measured. Most simulations produce voids, but they struggle to produce voids as large as boats. The statistical distribution of void sizes in the simulations is narrower than what is observed, with fewer extreme outliers. This discrepancy could indicate that the simulations are missing some ingredients, a form of feedback that expels gas more efficiently, a variation in dark energy that enhances the growth of voids, a quirk in the initial conditions that allowed certain regions to become more underdense than average. Or it could indicate that the observations themselves are incomplete, that the voids we measure are not as extreme as they appear, that selection effects or measurement errors have biased our perception of their properties. Resolving this discrepancy requires better data and better models, a cycle of observation, simulation, and refinement that has characterized cosmology for decades. Each generation of surveys reveals new structures, and each generation of simulations attempts to reproduce them. The void is part of this ongoing dialogue between theory and observation, a reminder that the universe is not yet fully understood, that the map is not yet complete, that there are still regions of silence we are only beginning to measure. The effort to map the Boötes Void, then, is not merely a technical exercise. It is an investigation into the limits of knowledge, an exploration of how much we can infer from absence, and a test of whether our models of the universe can account for the full range of structures that exist. The void is silent, but that silence is not empty. It is filled with questions, with uncertainties, with the faint echoes of processes that have yet to be named. And measuring that silence, tracing its boundaries, understanding its origins, this is the work that continues, patient and precise. In observatories around the world, as astronomers piece together the map of what is not there. The night sky above Kitt Peak, Arizona, in 1981 looked no different than it had for millennia. The stars wheeled overhead in their familiar patterns, the Milky Way stretched across the darkness, and the constellation boats hung in the northern hemisphere, unremarkable to the unaided eye. But inside the dome of the Mayall telescope, 4 astronomers were collecting data that would reveal something unprecedented, something that should not have existed according to the prevailing understanding of the universe. Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman were conducting a redshift survey, a methodical effort to map the three-dimensional distribution of galaxies in a specific region of the sky. The project was part of a broader initiative to understand cosmic structure, to move beyond simple catalogs of galaxy positions and measure how far away each galaxy was, constructing a true map of space rather than a flat projection. The work was tedious. Each galaxy required careful observation, its light captured and dispersed through a spectrograph to reveal the telltale redshift that would indicate its distance. The team had chosen the boat's region not because it was special, but because it was convenient high in the sky during certain seasons. Relatively free of foreground stars that might complicate observations, the data accumulated slowly. Galaxy after galaxy was measured, plotted on a chart that showed distance versus position. Patterns began to emerge. Galaxies clustered together in some regions as expected. Filamentary structures appeared, connecting clusters across tens of millions of light-years. The universe, as seen through this narrow slice, looked roughly as theory predicted lumpy, structured but not wildly irregular. And then, abruptly, the galaxies stopped. At first, it seemed like an error. Perhaps the telescope had drifted off target, or the exposures had been too short to detect the fainter galaxies in that region. But when the observations were repeated, the result was the same. For a vast stretch of space, corresponding to more than 300 million light-years, there were almost no galaxies. The redshift survey had cut through a region of profound emptiness, a void so large that it challenged every expectation the team had brought to the project. The initial reaction was caution. Astronomy is a discipline built on skepticism, where extraordinary claims require extraordinary evidence. A void of this size was not merely unusual. It was, by the standards of the time, nearly impossible. The prevailing models of structure formation allowed for voids, certainly, but they predicted them to be modest in scale. Gaps between filaments in the cosmic web, not spherical cavities large enough to swallow thousands of galaxies. The team knew that if they published this finding, it would be scrutinized intensely. They needed to be certain. The next step was to rule out observational biases. Could the void be an artifact of the survey method? Redshift surveys at the time were limited in sensitivity. They could detect only the brightest galaxies. And if the void happened to contain an unusually high proportion of faint, low-luminosity galaxies, the survey might have missed them. To test this, the team conducted deeper observations, using longer exposure times to probe for dimmer objects. They found a few additional galaxies, but not nearly enough to fill the void. The underdensity was real. Another possibility was that the void was not spherical, but elongated tunnel-like structure aligned by chance with the survey's line of sight, creating the illusion of a larger, more symmetric emptiness. To address this, the team expanded their observations, measuring redshifts in adjacent regions of the sky to map the void's boundaries in multiple directions. The data confirmed that the void was indeed roughly spherical, extending far beyond the original pencil beam survey. It was not an optical illusion or a quirk of perspective. It was a genuine three-dimensional structure, an absence carved into the fabric of the cosmos. As the evidence accumulated, the team prepared to publish their findings. The paper submitted in 1981 described the void in careful, measured language, presenting the data without overstating its implications. But the implications were clear. If the void was real land, the data strongly suggested it was. then the universe was not as homogeneous as cosmologists had assumed. The cosmological principle, the foundational idea that the universe looks the same on large scales in all directions, appeared to have exceptions. The void was an anomaly, a deviation so significant that it could not be easily explained by the standard models of structure formation. The reaction from the broader scientific community was mixed. Some astronomers were intrigued, seeing the void as an opportunity to test and refine cosmological theories. Others were skeptical, suspecting that the void was either a statistical fluke or the result of incomplete observations. The prevailing sentiment was one of discomfort. Cosmology at that time was emerging from a period of uncertainty, consolidating around a new framework that included dark matter and inflationary theory. The discovery of a supervoid threatened to destabilize this emerging consensus, introducing a new puzzle just as the old one seemed to be resolving. Follow-up studies were inevitable. Other research groups targeted the Boötes region with their own telescopes, using different instruments and techniques to verify the finding. Some conducted wider surveys, mapping the void's surroundings to understand its context within the larger cosmic web. Others used deep imaging to search for faint galaxies that might have been missed. Still others looked for indirect signs of matter-gas clouds, dark matter halos, anything that might indicate the void was less empty than it appeared. These studies confirmed the void's existence, but they also revealed its complexity. The void was not completely empty. A few dozen dwarf galaxies were scattered throughout, along with diffuse clouds of intergalactic gas. But the overall density was astonishingly low, perhaps 10% of the average density of the universe. The void's boundaries were not sharp, but gradual, transitioning over millions of light-years from the underdense interior to the overdense filaments beyond. And the void's shape, while roughly spherical, had subtle asymmetries. Hints of structure that suggested its formation had not been perfectly uniform. The confirmation of the void's reality did not immediately resolve the questions it raised. If anything, it deepened them. The existence of such a large underdensity implied that the initial conditions of the universe, the tiny fluctuations in density imprinted during the first moments after the Big Bang, were more variable than the cosmic microwave background suggested. Or it implied that the processes governing structure formation were more complex, capable of amplifying small fluctuations into extreme configurations that the simplest models did not predict. Either way, the void demanded an explanation, and no explanation was immediately forthcoming. One response was to incorporate the void into simulations of structure formation. By the mid-1980s, cosmologists were beginning to use computers to model how the universe evolved from its smooth initial state to the clumpy, structured cosmos we observe. These simulations tracked the motions of millions of particles representing dark matter, watching as gravity pulled them together into filaments and clusters while leaving voids behind. When the simulations were run, they did produce voids, but none as large as the Boötes Void. The statistical distribution of void sizes in the simulations peaked at smaller values, with extreme outliers, like Boötes, occurring only rarely, if at all. This discrepancy suggested that something was missing from the models. Perhaps the initial conditions were not as uniform as assumed. Perhaps the physics of structure formation included processes that the simulations did not account for: feedback from supernova, the influence of magnetic fields, the effects of cosmic rays. Or perhaps the void was simply a rare statistical fluctuation, an event so improbable that it occurred only once or twice in the observable universe. This last explanation was unsatisfying, but it could not be ruled out. The universe is large, and rare events do happen. The question was whether the Boötes Void was truly rare, or whether it was the first of many such structures waiting to be discovered. The paradigm shift triggered by the void's discovery was not immediate. Scientific revolutions rarely are. They unfold over years as evidence accumulates, as alternative explanations are tested and discarded, as the community gradually adjusts its assumptions to accommodate the new data. In the case of the Boötes Void, The shift involved a recognition that voids were not merely passive features of the cosmic web, but active components that needed to be understood in their own right. They were not just gaps between filaments, but structures with their own properties, their own formation histories, their own role in shaping the universe's evolution. This recognition changed the way astronomers conducted surveys. Instead of focusing exclusively on galaxies and clusters, they began to map voids systematically, measuring their sizes, shapes, and internal properties. They looked for correlations between voids and other features of the cosmic web, searching for patterns that might reveal the underlying physics. They compared observations to simulations, using voids as a test of cosmological models. And they discovered that the Boötes Void was not unique. Other supervoids were found, some even larger, scattered throughout the observable universe. Each new discovery reinforced the idea that voids were not anomalies, but integral features of cosmic structure. The historical significance of the Boötes Void lies not just in what it revealed about the universe, but in how it challenged the process of scientific inquiry itself. The void was discovered by accident, a byproduct of a survey designed to map galaxies, not to find empty spaces. Its existence was initially met with skepticism because it contradicted prevailing assumptions, and its confirmation required years of follow-up observations, conducted by independent teams using different methods before the community accepted it as real. This sequence: accidental discovery, initial skepticism, gradual confirmation, is characteristic of how science responds to the unexpected. The void also illustrated the limits of theory. Cosmology, for all its mathematical sophistication, is ultimately an empirical science. Theories must conform to observations, not the other way around. When observations reveal something that theories do not predict, the theories must be revised. The Boötes Void was one such revelation, a reminder that the universe is under no obligation to behave according to human expectations. It can produce structures that seem impossible, configurations that strain the boundaries of probability, features that force us to reconsider what we thought we knew. In the years following the discovery, Robert Kirshner and his colleagues reflected on the significance of their finding. They had not set out to challenge cosmology or to discover something revolutionary. They had simply been mapping galaxies, following a standard observational procedure, when the data revealed something unexpected. The void was there all along, invisible to previous generations of astronomers, because the tools to detect it did not exist. It took a redshift survey, a three-dimensional mapping technique, to reveal the absence hidden in plain sight. And once revealed, the void could not be ignored. It became a fixture of cosmology, a landmark in the map of the universe, a structure that every model of structure formation had to account for. The discovery also had a personal dimension. For Kirshner and his team, the void represented years of their lives, years spent collecting data, analyzing observations, defending their findings against skeptics. It was work that required patience, precision, and a willingness to trust the data even when it contradicted expectations. They could not know, at the outset, that their survey would uncover something so significant. They could only follow the evidence wherever it led and present their conclusions with as much rigor as possible. The void, in this sense, was a testament to the value of careful, systematic observation, to the idea that science progresses not through grand theories alone, but through the slow accumulation of data, one galaxy at a time. The intellectual atmosphere of 1981 was one of optimism, tempered by uncertainty. Cosmology was becoming a precision science, with new instruments and techniques allowing astronomers to probe the universe in unprecedented detail. The cosmic microwave background had been mapped, confirming the Big Bang model. Dark matter had been proposed as a solution to the problem of galaxy rotation curves. Inflationary theory had been introduced to explain the uniformity and flatness of the universe. The pieces of a comprehensive cosmological framework were falling into place. And then the Boötes Void appeared, a piece that did not quite fit, a reminder that the puzzle was not yet complete. The void's discovery did not overturn cosmology, but it complicated it. It added a new constraint that models had to satisfy, a new feature that simulations had to reproduce. It forced cosmologists to ask whether the universe was as smooth, as predictable, as statistically well-behaved as they had assumed. And it suggested that there might be other surprises waiting to be found. Other structures lurking in the data, invisible until the right survey came along. The void was a hole in the sky, yes, but it was also a window, a glimpse of the universe's capacity to surprise, to confound, to reveal itself in ways that no theory had anticipated. And in that sense, it was not just a discovery, but a reminder that the cosmos is still, in many ways, unknown. A void, once formed, does not remain static. It grows. The same forces that carved out the initial underdensity continue to operate. And in the absence of matter to anchor the region gravitationally, the void expands. This expansion is not driven by an explosion, not by matter fleeing outward from a central point, but by the fundamental dynamics of the universe itself, interplay between gravity, which pulls matter together, and the expansion of space, which pushes everything apart. In regions where galaxies cluster densely, gravity dominates, holding structures together despite the universe's expansion. But in voids where matter is sparse, gravity is weak, and the expansion proceeds unimpeded, accelerating as the void grows larger and emptier. This process is sometimes called the void push effect, though the name is somewhat misleading. There is no literal push, no force emanating from the void center. Rather, the void grows because matter at its edges is pulled away by the gravitational attraction of the surrounding filaments and clusters. As this matter flows outward, the void's interior becomes even less dense, and the expansion accelerates. It is a positive feedback loop, a runaway process in which underdensity begets further underdensity. Emptiness begets further emptiness. The void does not expand into space. Space itself expands within the void, stretching the distances between the few galaxies that remain. But there is another force at work, one that has only recently been recognized as central to the universe's evolution: dark energy. The mysterious component that makes up roughly 70% of the universe's total energy content exerts a repulsive effect, driving the accelerated expansion of space. Unlike gravity, which diminishes with distance and depends on the presence of mass, dark energy is thought to be uniform, present everywhere in equal measure, a property of the vacuum itself. In regions filled with matter, dark energy's effects are subtle, overshadowed by the gravitational pull of galaxies and clusters. But in voids where matter is scarce, dark energy dominates. The behavior of dark energy in voids is one of the most intriguing aspects of modern cosmology. If dark energy is truly uniform, then its influence should be the same everywhere, regardless of whether a region is dense or empty. But the observable consequences differ dramatically. In a galaxy cluster where gravity is strong, dark energy contributes to the overall expansion of the universe but does not disrupt the cluster's internal structure. The galaxies within the cluster remain bound together, their mutual gravitational attraction overwhelming the repulsive effect of dark energy. In a void, however, there is nothing to counteract dark energy. The few galaxies present are too far apart, their gravitational influence too weak to resist the expansion. The void grows, and as it grows, the density within it drops, allowing dark energy to exert an even greater influence. This dynamic suggests that voids are not passive remnants of structure formation, but active participants in the universe's evolution. They are regions where dark energy's effects are most visible, where the repulsive force that drives the universe's acceleration manifests most clearly. In this sense, the Boötes Void is not merely an empty space, but a laboratory for studying dark energy, a place where the competition between gravity and expansion plays out with unusual clarity. One hypothesis that has gained traction in recent years is that the Boötes Void did not form as a single, coherent structure, but as a result of multiple smaller voids merging together. This idea is motivated by simulations of structure formation, which show that voids do not emerge fully formed, but grow over time through a process of coalescence. In the early universe, matter was distributed with small variations in density. Regions that were slightly less dense than average became protovoids, expanding as matter flowed away. As the universe evolved, these protovoids grew and began to overlap. Where two voids met, the boundary between them dissolved, creating a larger, more irregular structure. Over billions of years, this process repeated, with smaller voids merging into larger ones, gradually producing the supervoids we observe today. The Boötes Void, according to this model, may be the product of several such mergers. Its spherical shape, which seems so anomalous, could be the result of multiple voids expanding and blending together, smoothing out the irregularities that would characterize a single, isolated void. The lack of galaxies within it could be explained by the cumulative effect of these mergers, each one expelling matter more efficiently than a single void could on its own. And the void's extreme size could be understood as the end result of a process that has been ongoing since the early universe, amplifying an initial underdensity into a colossal cavity. This merger hypothesis is difficult to test directly because we cannot observe the void's history. We see only its current state, a snapshot of a process that has unfolded over billions of years. But there are indirect ways to probe the void's past. One approach is to examine the distribution of galaxies around the void's edges. If the void formed through mergers, the surrounding regions should show signs of this history irregularities in the distribution of matter. Streams of galaxies that trace the paths along which material flowed away from the protovoids. Another approach is to look for variations in the void's internal structure. A void formed through mergers might not be perfectly uniform inside, but could contain faint traces of the boundaries where smaller voids once met, regions of slightly higher density that mark the remnants of earlier structures. Observations have revealed some evidence consistent with the merger scenario. The Boötes Void's boundaries are not perfectly smooth, but show localized overdensities, knots of galaxies that may represent the edges of the original protovoids. The void's interior, while extremely underdense, is not completely homogeneous. There are subtle gradients in galaxy density, variations that could be the faint signatures of a complex formation history. And the void's location within the cosmic web suggests that it sits in a region where multiple filaments converge, creating a natural setting for the coalescence of smaller voids into a larger structure. The violence of this process, if it can be called violence, is slow motion by human standards. Voids do not collide like galaxies, producing shock waves and bursts of star formation. They merge gradually, over hundreds of millions of years, as the expansion of space erases the boundaries between them. There is no dramatic event, no moment of impact. The voids simply grow into one another, their interiors blending seamlessly, until what were once separate structures become indistinguishable parts of a single, larger void. It is a process of erasure rather than creation, a gradual simplification of cosmic structure as the universe ages. Yet this simplification is not random. It follows rules governed by the distribution of matter in the early universe and the laws of physics that dictate how that matter evolves. Dark energy plays a central role, but it does not act alone. The initial fluctuations in density, imprinted during the inflationary epoch, determine where voids will form and how large they can grow. Gravity shapes the flow of matter, channeling it along filaments and into clusters, leaving behind the underdense regions that become voids. And the expansion of space provides the backdrop against which all of this unfolds, stretching distances, diluting densities, and allowing dark energy's influence to grow over time. The interplay between these forces creates a universe that is neither purely random nor perfectly ordered. Structure emerges from chaos, but the structures that form are constrained by the initial conditions and the physical laws that govern their evolution. Voids are part of this structure, as essential to the cosmic web as the filaments and clusters that surround them. They are the empty spaces that define the boundaries of the web, the low-density regions that give shape to the high-density regions. Without voids, the cosmic web would not exist as we observe it. The universe would be more uniform, less interesting, less capable of supporting the diversity of environments in which galaxies and life can arise. The Boötes Void, then, is not merely an absence. It is a consequence of the universe's expansion, a product of dark energy's dominance in regions where gravity is weak. It is a structure shaped by mergers, by the coalescence of smaller voids into a larger one, by the slow-motion dynamics of cosmic evolution. And it is a window into the future. As the universe continues to expand, as dark energy exerts an ever greater influence, voids will grow larger and emptier. The filaments that currently define the cosmic web will thin and stretch, and eventually, they too will dissolve, leaving behind a universe dominated by vast, empty regions separated by immense distances. This future is billions of years away, too distant to observe directly, but its inevitability is written in the physics of dark energy. If dark energy remains constant, it is indeed a cosmological constant, a fixed property of space, then the universe's expansion will continue to accelerate. Galaxies outside our local group will recede beyond the horizon of visibility, their light redshifted into invisibility. The cosmic microwave background will cool and fade. And the voids, already the dominant feature of the universe by volume, will expand until they encompass nearly everything. The Boötes Void, in this sense, is a preview of the cosmos to come, a glimpse of the universe's ultimate fate. But this fate is not certain. Dark energy remains one of the greatest mysteries in cosmology, and its properties are not fully understood. If dark energy is not constant, it varies over time or from place to place, then the future could be different. The universe's expansion might slow, allowing gravity to reassert itself and halt the growth of voids. Or the expansion might accelerate even more dramatically, tearing apart not just the cosmic web, but galaxies, stars, and eventually atoms themselves in a scenario known as the Big Rip. The behavior of voids, their growth rates and internal dynamics, provides one of the few observational handles we have on dark energy's properties, making the study of structures like the Boötes Void essential to understanding the universe's ultimate trajectory. The mechanics of cosmic voids, then, are not just a matter of abstract physics. They have implications for the universe's past, present, and future. They tell us how structure formed, how it evolves, and where it is heading. They reveal the balance of forces that shapes the cosmos. The competition between gravity and expansion, between matter and dark energy. And they remind us that the universe is dynamic, not static, that the structures we observe today are not eternal but transient, products of a specific epoch in cosmic history. The Boötes Void is winning the battle against gravity. This is perhaps the most striking aspect of its existence. In most regions of the universe, gravity dominates on local scales, pulling matter together, forming stars and galaxies, creating the structures we associate with cosmic beauty and complexity. But in the void, gravity has lost. There is too little matter for it to work with, too much space for it to bridge. Dark energy, the force of expansion, reigns supreme, and the void grows larger with each passing moment. It is a region where the universe's tendency toward emptiness, toward cold and darkness, is most evident. Yet this emptiness is not featureless. It is structured, shaped by the same forces that govern the rest of the cosmos. The void has boundaries marked by the transition from underdense to overdense regions. It has internal variations, subtle gradients in density that hint at its formation history. And it has a geometry, a shape that reflects the processes that created it. The void is not nothing. It is a specific configuration of space and matter, a solution to the equations of cosmology, a state that the universe has settled into through billions of years of evolution. Understanding the mechanics of voids requires integrating insights from multiple areas of physics. General relativity provides the framework for understanding how matter and energy curve spacetime, how gravity operates, and how the universe expands. Quantum field theory offers a possible explanation for dark energy, suggesting that it arises from the vacuum energy of empty space, the quantum fluctuations that pervade even the most barren regions. Hydrodynamics and thermodynamics govern the behavior of gas within and around voids, determining how it cools, heats, and flows. And statistical mechanics helps us to understand the formation of structure, the amplification of fluctuations, and the emergence of patterns from the initial conditions of the Big Bang. The Boötes Void sits at the intersection of all these disciplines. It is a test case for general relativity, a probe of dark energy, a laboratory for studying the evolution of cosmic structure. It challenges our models and forces us to refine our understanding of how the universe works. And it does so not by being exotic or unusual in the sense of violating known physics, but by being an extreme example of processes that operate everywhere. The void is not an anomaly. It is the universe taken to its logical conclusion, a place where the forces that shape the cosmos are allowed to play out with minimal interference, producing a structure that is as much a part of the natural order as any galaxy or star. In this way, the void reveals itself not as an enemy of structure, but as a complement to it. It defines the spaces between the filaments, giving the cosmic web its shape. It provides a contrast that makes the overdense regions stand out, a baseline against which the richness of galaxy clusters can be measured. And it demonstrates that the universe's architecture is not homogeneous, but varied, capable of producing both the densest environments and the most barren, both the brightest galaxies and the darkest voids. The Boötes Void is an active growing entity, expanding as the universe ages, pushed outward by dark energy shaped by the mergers of smaller voids, and ultimately destined to grow even larger as the cosmos continues its inexorable expansion into the deep future. 60 galaxies. In a volume of space 330 million light-years across, a region that should contain thousands upon thousands of star systems, there are only 60. They drift through the void like ships on an empty ocean, separated by distances so vast that their light takes tens of millions of years to reach one another. If an observer stood on a planet orbiting a star in one of these galaxies, the night sky would be profoundly different from our own. There would be no neighboring galaxies visible to the naked eye, no Andromeda spiral hanging in the heavens, no Magellanic clouds marking the southern sky. The universe beyond would be a distant, faint mystery, detectable only with the most powerful instruments. These are the loneliest galaxies in the known cosmos, and their very existence poses questions that standard models of galaxy formation struggle to answer. Isolation shapes evolution. On Earth, species that develop on remote islands often diverge from their mainland relatives, adapting to environments free from predators and competitors. The same principle applies to galaxies. Most galaxies in the universe live in crowded environments, groups, clusters, filaments where interactions are common. Galaxies merge, tearing stars from one another, triggering bursts of star formation, disrupting spiral arms, and transforming elegant disks into chaotic ellipticals. They pass through the hot, dense gas that fills galaxy clusters, experiencing ram pressure stripping that removes their fuel for star formation. They feel the gravitational pull of neighbors, experiencing tidal forces that stretch and distort their shapes. In these dense environments, a galaxy's evolution is shaped as much by external forces as by its own internal dynamics. The galaxies of the Boötes Void have experienced none of this. They formed in isolation and have remained isolated for billions of years. There have been no mergers, no tidal interactions, no stripping of gas by external pressure. These galaxies have evolved solely according to their own internal processes, governed by the interplay between gravity, gas dynamics, and star formation within their own boundaries. They are, in a sense, cosmic control groups, examples of what galaxies look like when the universe leaves them alone. The differences are striking. Many of the void galaxies are late-type spirals, rich in gas and actively forming stars at rates higher than galaxies of comparable mass in denser environments. This is counterintuitive. In most regions of the universe, star formation is suppressed in isolated environments. Because there is no mechanism to compress the gas, no interactions to trigger the collapse of molecular clouds. But the void galaxies seem to have retained their gas reservoirs over cosmic timescales, suffering no losses from external stripping, and they continue to convert that gas into stars with surprising efficiency. Their isolation has preserved them, allowing them to maintain the conditions for star formation long after their counterparts in denser regions have exhausted their fuel. Their shapes, too, are unusual. While many void galaxies are spirals, they often exhibit irregular morphologies, lopsided disks, asymmetric spiral arms, clumpy distributions of young stars. These asymmetries suggest that the galaxies are not in equilibrium, that they are still settling, still adjusting to the dynamics of their own rotation and gravity. In denser environments, such irregularities are typically smoothed out by interactions with neighbors. But in the void, there are no neighbors to exert such influence. The galaxies remain in states that would be transient elsewhere, frozen in configurations that reveal the details of their formation and early evolution. The question of how these galaxies formed in the first place is one of the deepest mysteries of the Boötes Void. Galaxy formation requires gas, hydrogen, and helium from the early universe, cooling and condensing within dark matter halos. In typical regions of space, this gas flows along filaments, channeled by gravity toward the densest regions where galaxies assemble. But the Boötes Void is not typical. It is profoundly underdense, with little matter to provide the raw material for galaxy formation. Where did the gas that formed these 60 galaxies come from? And why did it remain in the void, rather than flowing outward toward the surrounding filaments? One possibility is that the gas was already present when the void began to form, trapped within small dark matter halos that were too weak to resist the void's expansion, but strong enough to retain their gas. As the void grew, most of the matter flowed away, but a few halos, perhaps those that were slightly denser than average, or those that happened to be located in regions where the outflow was weaker, managed to hold on to their gas and eventually form galaxies. This scenario requires a delicate balance. The halos must be massive enough to retain gas against the expansion of the void, but not so massive that they attract additional matter and cease to be isolated. The fact that only 60 galaxies formed suggests that this balance was achieved only rarely, that the conditions for galaxy formation in the void were exceedingly stringent. Another possibility is that the gas was delivered to the void later, through the accretion of material from the surrounding filaments. Simulations of structure formation show that even voids are not completely disconnected from the cosmic web. There are tendrils of matter, faint streams of gas that connect the filaments to the void's interior, and it is conceivable that some of this gas could have been captured by dark matter halos within the void, providing the fuel for galaxy formation. This scenario implies that the void galaxies are relatively young, having formed not in the early universe but more recently, as the void matured and gas began to trickle inward. Observations of the void galaxies' stellar populations, the ages and compositions of their stars could test this hypothesis, revealing whether these galaxies are ancient or more recently assembled. A third possibility, more speculative, is that the void galaxies represent a different mode of galaxy formation altogether. In dense environments, galaxies form hierarchically, through the merger of smaller systems into larger ones. But in the void, where mergers are rare, galaxies might form monolithically, collapsing directly from large gas clouds without the intermediate steps of hierarchical assembly. This would produce galaxies with distinct properties, less centrally concentrated, more gas-rich, with stellar populations that reflect a single, extended episode of star formation, rather than the complex merger histories of typical galaxies. Some observations hint at such differences, but the data is limited and the interpretation remains uncertain. The isolation of the void galaxies also has implications for their dark matter content. In standard models of galaxy formation, the amount of dark matter in a galaxy's halo is determined by the density of the surrounding environment and the history of mergers the galaxy has undergone. Galaxies in clusters tend to have more dark matter relative to their luminous mass, because they have accreted material from their surroundings. Isolated galaxies, by contrast, should have less dark matter, having grown only through the gradual collapse of their initial halos. The void galaxies, being maximally isolated, should fall at the extreme end of this spectrum. They should be examples of galaxies whose dark matter halos have evolved in the simplest possible way, free from the complications of accretion and interaction. Measuring the dark matter content of void galaxies is challenging because the techniques rely on observing the motions of stars and gas within the galaxies, tracing the gravitational potential that holds them together. For distant galaxies, these measurements are difficult, requiring high-resolution spectroscopy and long observation times. But preliminary studies suggest that void galaxies do indeed have lower dark matter fractions than galaxies in denser environments, consistent with the idea that their halos have not been significantly modified by external processes. This finding supports the notion that the void galaxies are pristine examples of galaxy formation, uncontaminated by the complex dynamics that characterize most of the universe. The void galaxies also provide insights into the role of environment in regulating star formation. In dense regions, star formation is often quenched by external processes RAM, pressure stripping, tidal interactions, the presence of hot intracluster gas. In the void, none of these processes operate, and yet the void galaxies are not forming stars at arbitrarily high rates. They are limited by internal processes, by the availability of gas, the efficiency of converting gas into stars, and the feedback from supernova and stellar winds that heats the gas and prevents further collapse. By studying the void galaxies, astronomers can isolate these internal processes, measuring their effects without the confounding influence of environment. The void becomes a laboratory, a place where the intrinsic physics of galaxy formation can be observed in its purest form. One of the most intriguing aspects of the void galaxies is their color. Galaxies are often classified by their optical colors, which reflect the ages and types of stars they contain. Blue galaxies are dominated by young, massive stars and are actively forming new stars. Red galaxies are dominated by older, lower-mass stars and have largely ceased star formation. Most galaxies in the universe fall somewhere along this blue-red sequence, with environment playing a major role in determining where a galaxy sits. Dense environments tend to produce red galaxies, while less dense environments produce blue ones. The void galaxies are overwhelmingly blue, consistent with their high star formation rates and gas-rich nature. But there are exceptions, a handful of red galaxies scattered throughout the void. Galaxies that have somehow quenched their star formation, despite the absence of external mechanisms to do so. These red void galaxies are puzzling. How did they stop forming stars? One possibility is that they exhausted their gas reservoirs through star formation and stellar feedback, expelling or heating their remaining gas to the point where it could no longer collapse and form new stars. Another possibility is that they experienced some internal instability, a burst of star formation so intense that it drove away all the remaining gas, leaving behind a dead red galaxy. A third possibility is that these galaxies are not truly isolated, that they are remnants of small groups or pairs that merged early in the void's history, producing elliptical galaxies that have since drifted apart as the void expanded. Each of these scenarios makes different predictions about the galaxy's properties, their stellar masses, their gas content, their internal kinematic sand. Distinguishing between them requires detailed observations that are only now becoming feasible. The existence of the void galaxies also raises questions about the lower limits of galaxy formation. Is there a minimum density below which galaxies cannot form at all? The Boötes Void is close to this limit. if such a limit exists. The fact that 60 galaxies manage to form suggests that the threshold, if it exists, lies somewhere below the void's average density. But it also suggests that the threshold is not far below, that the void represents a regime where galaxy formation is marginal, occurring only in rare pockets where conditions were favorable. Understanding this threshold could provide insights into the fundamental requirements for galaxy formation, the minimum conditions needed for gas to cool, collapse, and ignite into stars. The void galaxies also serve as natural experiments in galactic archaeology. Because they have not undergone mergers, their stellar populations preserve a cleaner record of their formation histories. Each generation of stars carries information about the conditions under which it formed the density of the gas, the rate of star formation, the abundance of heavy elements. By studying the stellar populations of void galaxies, astronomers can reconstruct their histories in detail, tracing how they assembled their mass, how they enriched their gas with metals, and how they evolved over cosmic time. This is more difficult in galaxies that have undergone mergers, where the stellar populations from different progenitor galaxies are mixed together, obscuring the individual histories. The void galaxies are also important for calibrating models of galaxy formation. These models, which simulate the evolution of galaxies from the early universe to the present, contain numerous parameters that must be tuned to match observations. By including isolated galaxies like those in the Boötes Void, astronomers can test whether the models correctly capture the physics of galaxy formation in extreme environments. If the models fail to reproduce the properties of void galaxies, their star formation rates, their colors, their morphologies, it suggests that the models are missing some key process, some aspect of galaxy evolution that is important in low-density environments. The 60 galaxies of the Boötes Void are not merely curiosities. They are windows into a mode of cosmic evolution that is rarely accessible elsewhere. They show us what galaxies look like when the universe does not interfere, when the chaotic processes that dominate most regions of space are absent. They are cosmic hermits, isolated and self-contained, evolving according to their own internal logic. And in their isolation, they reveal truths about galaxy formation that would be hidden in more crowded environments. They are laboratories without walls, experiments conducted by the universe itself, and they offer insights that no simulation or theoretical model can fully replicate. The void, for all its emptiness, has preserved these galaxies as relics of a simpler time, as examples of what the universe produces when left entirely alone in the dark. The universe is not static. It expands, and that expansion is accelerating. Every second, space stretches, carrying galaxies away from one another at velocities that increase with distance. This acceleration is driven by dark energy, the invisible force that permeates the cosmos, pushing against the inward pull of gravity. For now, the effects are subtle on human scales, imperceptible even within our own galaxy. But on the largest scales between galaxy clusters across supervoids, the acceleration is undeniable, and it is relentless. The Boötes Void offers a glimpse of what this acceleration means for the future. It is a region where dark energy has already triumphed over gravity, where the expansion of space has overwhelmed the forces that hold structure together. The void is not an anomaly in the sense of being disconnected from the rest of the universe. It is, instead, a preview, an early manifestation of a process that will eventually claim the entire cosmos. The void shows us what happens when matter is too sparse, when distances are too great, when gravity loses its ability to counteract the expansion. And if current models of dark energy are correct, this is the fate that awaits every region of space. The universe, in time, will become a collection of voids, each one as empty and vast as Boötes. The timeline for this transformation is measured not in millions, but in trillions of years. At present, the universe is roughly 14 billion years old, still in its youth by cosmological standards. Galaxies are forming stars, Clusters are held together by gravity, and the cosmic web remains visible. But this will not last. As the universe ages, as space continues to expand, the web will thin. Filaments will stretch, becoming more tenuous until they can no longer sustain the flow of gas that feeds galaxy formation. Clusters will become isolated, separated by distances so vast that light from one cluster will never reach another. And eventually, even the clusters themselves will dissolve. Their member galaxies drifting apart as the expansion of space overcomes their mutual gravitational attraction. The Boötes Void, in this context, is not an outlier. It is a harbinger. It shows us the end state of structure in a universe dominated by dark energy. In the far future, every galaxy will find itself in a void as empty and lonely as the one that now surrounds the 60 isolated galaxies of Boötes. The night sky, from the perspective of any observer in such a galaxy, will be completely dark. There will be no neighboring galaxies, no distant clusters, no cosmic microwave background by then. The radiation from the Big Bang will have red-shifted into undetectability. The universe will appear finite, bounded by the horizon of visibility, even though it is infinite in extent. Each galaxy will be alone, an island of light in an ocean of darkness that stretches without end. This fate is sometimes called the Big Freeze, though the term is misleading. The universe will not freeze in the sense of stopping. It will continue to expand, to cool, to evolve. But the processes that drive cosmic activity, star formation, galactic interactions, the cycles of matter and energy that sustain complexity will gradually cease. Stars will exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will fade as their stellar populations age and no new stars are born. And the universe will settle into a state of maximum entropy, a configuration in which energy is evenly distributed where no gradients exist to drive change where nothing of interest happens because there is no free energy left to power it. The void, then, is a laboratory for studying this end state. It is a region where the conditions of the far future already exist, where the density is so low that the dynamics resemble those of a universe much older than our own. By observing the void, by measuring its properties and understanding its evolution, astronomers can test their models of how the universe will behave as it ages. The void is not merely a gap in the present structure of the cosmos. It is a window into the future, a place where the long-term consequences of dark energy are already visible. But the void also raises deeper questions about the nature of the vacuum itself. In classical physics, a vacuum is simply empty space, devoid of matter and energy. But in quantum mechanics, the vacuum is not empty. It seethes with activity, filled with virtual particles that flicker in and out of existence, borrowing energy from the uncertainty principle and returning it in timescales too brief to measure directly. This quantum vacuum energy is thought to be the source of dark energy, the force driving the universe's acceleration. If this is correct, then the vacuum is not nothing. It is something, a field, a state, a medium with properties that influence the behavior of the cosmos. The Boötes Void, with its near-perfect emptiness, is one of the few places where the properties of the vacuum can be studied directly. In regions filled with matter, the effects of the vacuum are overwhelmed by the gravitational and electromagnetic forces exerted by galaxies, stars, and gas. But in the void, where matter is scarce, the vacuum's influence dominates. The void's expansion, its resistance to the inflow of matter, its role in shaping the cosmic web, all of these may be manifestations of the vacuum's intrinsic properties, clues to the nature of dark energy and the ultimate fate of the universe. Yet the vacuum remains enigmatic. Theoretical calculations of the vacuum energy, based on quantum field theory, yield a value that is catastrophically larger than what is observed. Larger by a factor of 10 to the power of 121, of the most embarrassing discrepancies in the history of physics. Something is wrong, either with the theory or with the way we measure the vacuum's effects. The Boötes Void does not resolve this discrepancy, but it provides a testing ground for alternative theories. If dark energy is not constant, if it varies in strength or changes over time, the void might show signs of such variation. Its expansion rate, its internal structure, its interaction with the surrounding cosmic web, all of these could carry signatures of the vacuum's true nature, waiting to be decoded. The shadow of dark energy extends beyond the void itself. It touches every aspect of the universe's future, shaping not just the large-scale structure, but the fate of individual galaxies, stars, and planetary systems. As the universe ages, as the expansion accelerates, the local group of galaxies, the cluster that includes the Milky Way, Andromeda, and several dozen smaller galaxies will remain bound together by gravity, forming a gravitationally isolated system. But beyond the local group, everything will recede. The Virgo cluster, currently a mere 50 million light-years away, will drift beyond the horizon of visibility. The cosmic web will disappear from view, and future astronomers looking out from the Milky Way billions of years from now will see a universe that appears empty, a void as vast as boats, with no sign that other galaxies ever existed. This raises a profound question. How much of the universe is already beyond our horizon, lost to observation because the expansion has carried it too far away for its light to reach us? The observable universe is finite, bounded by the distance light has traveled since the Big Bang, but the universe itself may be infinite, extending far beyond what we can see. If this is true, then there are regions of space that are already in a state similar to the Boötes Void regions, where galaxies are so isolated, so separated by the expansion, that they will never interact, never even be aware of one another's existence. The void, in this sense, is not just a preview of the future. It is a glimpse of what already exists in the unobservable reaches of the cosmos, a reminder that our view of the universe is limited by the speed of light and the finite age of space. The acceleration of the universe also has implications for the fate of structure on smaller scales. Stars, planets, and even atoms are held together by forces much stronger than gravity electromagnetic forces, the strong and weak nuclear forces. These forces are not affected by the expansion of space, at least not in the current epoch. But if dark energy continues to strengthen, if the acceleration increases, there may come a time when the expansion becomes so rapid that it begins to tear apart structures that are currently stable. This scenario, known as the Big Rip, is speculative and depends on the properties of dark energy being more extreme than current observations suggest. But it is not impossible. If dark energy is not a cosmological constant, if it grows over time, then the universe's expansion could eventually overcome not just gravity, but all the forces that hold matter together, dissolving galaxies, stars, planets, and ultimately, atoms themselves in a catastrophic unraveling of structure. The Boötes Void does not provide evidence for the Big Rip, but it does show us what happens when expansion dominates over gravity on large scales. It demonstrates that the universe is capable of creating regions where structure cannot form, where the conditions for complexity are absent, where the expansion wins decisively. And it suggests that the balance between expansion and contraction, between dark energy and gravity, is more delicate than we might have assumed. The void is a place where that balance has tipped in favor of expansion, and it offers a cautionary glimpse of what happens when the forces of dispersal overcome the forces of assembly. Yet, even in the void, even in a future universe dominated by emptiness and isolation, there may be phenomena we have not anticipated. The vacuum, if it is indeed a quantum field, could undergo transitions, shifting from one state to another, releasing energy in the process. Such transitions might seed new structures, new forms of complexity that arise not from the gravitational collapse of matter, but from the dynamics of the vacuum itself. This is speculative, far beyond the reach of current observation. But it is a reminder that the universe has surprised us before, and it may surprise us again. The void, for all its apparent simplicity, may contain subtleties that we have not yet recognized, processes that operate on timescales and energy scales we have not yet probed. The darkness that fills the Boötes Void is not absolute. It is permeated by the cosmic microwave background, the faint afterglow of the Big Bang, and by the diffuse glow of intergalactic light photons emitted by stars and scattered by dust, spread so thinly that they are barely detectable. There is also the invisible presence of dark matter, which does not emit light but exerts gravitational influence, and the pervasive field of dark energy, which shapes the expansion of space. The void is not empty in the strict sense. It is filled with fields, with radiation, with the subtle infrastructure of the cosmos. But it is empty of the structures that give the universe its richness: the galaxies, the stars, the planets, the complex chemistry that arises in dense environments. It is empty of the things that make the universe interesting, alive, capable of producing observers who can contemplate its nature. In this sense, the void is a reminder of the fragility of structure. The universe does not favor complexity. It favors entropy, dispersal, the leveling of gradients. Complexity arises only where conditions allow, where gravity can overcome the expansion long enough to pull matter together, where stars can form and shine, where planets can coalesce and atmospheres can evolve. These conditions are rare, even in the populated regions of the cosmos. In the void, they are nearly absent. And in the far future, as the universe ages and dark energy dominates, these conditions will become rarer still, until complexity is confined to isolated pockets surrounded by vast deserts of emptiness. The Boötes Void, then, is not just a feature of the universe's current structure. It is a symbol of the universe's trajectory, a signpost pointing toward the deep future when all structure will have dissolved, when the cosmos will consist of isolated galaxies drifting through an expanding void, each one a tiny island of order in a sea of increasing entropy. The void is the shadow cast by dark energy, the outline of the universe's ultimate fate. It is a place where the future has already arrived, where the processes that will shape the cosmos over trillions of years are already at work, and where the darkness, patient and inexorable, is winning its slow victory over the light. Yet even as the void reveals this fate, it does not foreclose the possibility of meaning. The universe will not end tomorrow, nor in 1 billion years, nor in 1 trillion. There is time vast, incomprehensible stretches of time for stars to burn, for life to emerge, for consciousness to explore and understand the cosmos. The void is a prophecy, but it is not a judgment. It tells us what the universe will become, but it does not diminish what the universe is now. The light still shines, the stars still form, the galaxies still cluster along filaments of dark matter. And in the void itself, those 60 lonely galaxies continue their slow dance through the darkness, forming stars, evolving, existing in defiance of the emptiness that surrounds them. They are reminders that even in a universe destined for cold and silence, there is room for beauty, for complexity, for the brief, improbable flourishing of order against the tide of entropy. The void is the future, but it is not yet the present. And in the space between now and then, the universe continues to unfold, vast and mysterious, shaped by forces we are only beginning to understand. We live on the surface of a rock, orbiting a star in a galaxy containing hundreds of billions of other stars, within a universe that stretches beyond comprehension. And yet, for all this abundance, for all the matter and energy that fills our immediate cosmic neighborhood, we are surrounded by emptiness. The space between stars is a vacuum. The space between galaxies is a deeper vacuum. And the space within the Boötes Void is emptiness taken to its logical extrema region where the distances are so vast, the matter so sparse that the concept of neighborhood loses all meaning. To be human is to exist as an improbable concentration of matter in a universe that favors dispersal. We are made of atoms forged in the cores of dying stars, organized into complex structures by forces that resist the natural tendency toward disorder. We live on a planet that orbits within the narrow habitable zone of a stable star, protected by a magnetic field and an atmosphere that shields us from the harsh realities of space. We are surrounded by the illusion of solidity, rock beneath our feet, air in our lungs, water in our oceans. But this solidity is an anomaly. The universe, in its totality, is mostly void. It's a matter we are made of, the matter that makes up every star and planet and galaxy, constitutes less than 5% of the universe's total content. The rest is dark matter and dark energy, invisible and intangible, shaping the cosmos through forces we barely understand. The Boötes Void reminds us of this reality in a way that our immediate surroundings do not. When we look at the night sky, we see stars, we see the Milky Way, we see the faint smudges of neighboring galaxies. The universe appears rich, populated, full of light. But this is an artifact of our location. We live in a filament of the cosmic web, a region where matter has accumulated, where galaxies cluster together, where the density is far above the average. If we were instead located within the Boötes Void, our perception of the universe would be radically different. The night sky would be almost featureless. The nearest galaxy would be tens of millions of light years away, invisible to the naked eye. We would grow up believing the universe was sparse, empty, fundamentally lonely. This thought experiment is more than a curiosity. It reveals how deeply our understanding of the cosmos is conditioned by our perspective. We assume the universe is filled with galaxies because that is what we see from our vantage point. But the Boötes Void shows us that this is not the norm. Most of the universe by volume is empty. The galaxies we observe are concentrated in a small fraction of space, clustered along filaments and walls, while the voids occupy the majority. We live in an oasis, and we mistake it for the entire landscape. The void also forces us to confront the limits of observation. Astronomy is the study of light, and light requires a source. We can map the universe only to the extent that galaxies exist to emit light, that quasars shine brightly enough to be detected, that the cosmic microwave background provides a faint backdrop against which structure can be measured. But the void is defined by the absence of sources. It is a region where our usual tools fail, where the techniques we have developed to study the cosmos fall silent. We can infer the void's existence from the galaxies that surround it, but we cannot observe it directly. It is a blind spot, a gap in our knowledge, a reminder that the universe contains features that resist direct observation. This limitation is not merely technical, it is philosophical. The void challenges the assumption that the universe is fundamentally knowable, that, given enough time and better instruments, we can eventually map every corner of the cosmos and understand every process that shapes it. The void suggests that there are aspects of the universe that may remain forever beyond our reach, not because they are hidden by distance or obscured by dust, but because they are defined by absence, by the lack of the very things we use to construct knowledge. How do you study what is not there? How do you measure emptiness? How do you draw conclusions from silence? Humanity's relationship with the void is also a relationship with time. The universe is expanding, and as it expands, the distances between galaxies grow. The voids grow larger, the filaments thin. The cosmic web, which now spans hundreds of millions of light-years, will eventually dissolve, leaving behind isolated galaxies separated by distances so vast that light from one will never reach another. This process is already underway. Galaxies beyond a certain distance are receding from us faster than the speed of light, carried away by the expansion of space, and they are disappearing beyond the horizon of visibility. In 1 trillion years, the observable universe will be much smaller than it is now. The distant galaxies we see today will have faded from view, their light redshifted into undetectability. And the beings who inhabit the universe then, if any exist, will look out and see a cosmos that appears emptier, lonelier, more void-like than the one we observe today. The Boötes Void, in this context, is a preview of the future. It is a place where the isolation that will eventually characterize the entire universe is already present. And it raises a question. What is our responsibility as observers, as beings capable of understanding the cosmos, to document what we see while we still can? The universe will not always be as visible as it is now. The stars will not always shine. The galaxies will not always be within reach. We exist in a brief window of cosmic history, a moment when the universe is old enough to have formed complex structures, but young enough that those structures remain visible. This is the era of astronomy, the epoch when observation is possible, when the universe reveals itself to those who look. The responsibility to observe is not a burden, but a privilege. We are the universe's way of knowing itself, the improbable outcome of billions of years of cosmic evolution. That has produced beings capable of asking questions about their origins and their place in the vastness of space. The Boötes Void, for all its emptiness, is part of the story we are privileged to witness. It is a feature of the cosmos that exists whether or not we observe it. But it becomes meaningful only through observation, through the act of measuring, mapping, and attempting to understand. The void does not care that we study it, but we care. And that caring, that curiosity, is what makes us human. The void also invites us to reconsider what we mean by nothing. In everyday language, nothing is the absence of something, a negation, a blank space. But in cosmology, nothing is more complex. The vacuum is not truly empty. It is filled with quantum fields, with fluctuations that give rise to virtual particles, with the pervasive influence of dark energy. The void, similarly, is not a perfect vacuum. It contains galaxies, gas, dark matter, radiation. It is less dense than surrounding regions, but it is not devoid of content. And yet, we call it a void, a nothing, because it lacks the structures we associate with cosmic significance, the clusters, the filaments, the dense environments where galaxies interact and stars form. The void challenges us to recognize that nothing is, in fact, something. It is a state, a configuration, a region of the universe with its own properties and its own role in the cosmic architecture. This recognition has implications beyond cosmology. It touches on fundamental questions in philosophy and physics. What is the nature of existence? What does it mean for something to be real? The void exists, but it is defined by absence. It is real, but it lacks the qualities we typically associate with reality. It is a place, but it is a place where almost nothing happens. These paradoxes are not merely semantic. They reflect deep ambiguities in our understanding of the cosmos. Uncertainties about what constitutes structure, what counts as a phenomenon, and how we should classify the features of the universe. The Boötes Void also speaks to the limits of human perception and cognition. Our brains evolved to navigate a world of objects, trees, animals, tools, and they are optimized for detecting presence, not absence. We see what is there, and we struggle to comprehend what is not. The void, as a concept, requires a cognitive shift, an inversion of our usual way of perceiving the world. It asks us to attend to the spaces between things, to recognize that the gaps are as important as the objects that define them. This is not natural. It is learned, and it is difficult. But it is necessary if we are to understand the universe as it truly is, rather than as our instincts lead us to perceive it. The isolation of the void mirrors, in some ways, the isolation of the observer. To study the cosmos is to grapple with distances that dwarf human experience, timescales that exceed human lifetimes, and scales that render individual existence almost insignificant. We are alone on our planet, separated from the nearest star by a gulf of light years, from the nearest galaxy by millions of light years, from the edge of the observable universe by billions. And yet, we look outward, we measure, we theorize, we try to make sense of the vastness. The void, with its extreme emptiness, its profound distances, its silence, is a reflection of that cosmic loneliness, a reminder that the universe is not built on a human scale. that it does not care about our presence or our understanding. But the loneliness is not without beauty. The void is beautiful in its simplicity, in its geometry, in the way it reveals the underlying order of the cosmos. It is beautiful in the questions it raises, in the mysteries it preserves, in the way it resists easy explanation. And it is beautiful in its indifference, in the fact that it exists regardless of whether we observe it, that it was here long before we appeared and will remain long after we are gone. The void is a monument to the universe's capacity for emptiness, a testament to the fact that existence does not require fullness, that the cosmos can be as profound in its absences as in its presences. The future of astronomy will be shaped by voids. As the universe expands, as the cosmic web thins, astronomers will increasingly study regions of emptiness rather than regions of abundance. The techniques that work today, redshift surveys, gravitational lensing, quasar absorption spectroscopy, will need to be adapted to environments where sources are rare and signals are weak. New methods will need to be developed. Methods that can probe the properties of the vacuum, that can measure the influence of dark energy, that can detect the faint signatures of structure in regions where almost nothing exists. The void, once an anomaly, will become the norm, and our understanding of the cosmos will need to shift accordingly. There is also the question of what we will lose. As galaxies recede beyond the horizon, as the observable universe shrinks, future astronomers will have access to less information than we do. They will not see the distant quasars that reveal the universe's expansion history. They will not see the galaxy clusters that map the cosmic web. They will not see the cosmic microwave background as clearly as we do, because it will have cooled and faded. They will inherit a universe that appears smaller, emptier, less informative than the one we observe today. And they may draw different conclusions, construct different theories, based on the diminished view they have. This is a humbling thought. It suggests that our understanding of the cosmos is contingent on the era in which we live, that the universe reveals different aspects of itself at different times, and that there may be truths about the cosmos that are accessible to us now, but will be lost to future generations. The Boötes Void, then, is not just a scientific puzzle. It is a meditation on presence and absence, on knowledge and ignorance, on the fleeting nature of observation in an expanding universe. It is a reminder that the cosmos is vast and indifferent, that it contains more emptiness than substance, that the structures we see are rare and temporary. And it is an invitation to appreciate what we have while we have it, the stars in the sky, the galaxies beyond, the cosmic web that traces the architecture of everything that exists. We live in a universe that is still visible, still populated, still rich with light. The void shows us what the alternative looks like: a universe dominated by darkness, by distance, by the silence of empty space. It is a vision of the future, but it is also a call to the present, a reminder to look up, to observe, to understand, while the neighbors in the sky are still within reach. The mystery of the Boötes Void remains unsolved, but its existence alone is enough to change how we see the cosmos. It is a silent testament, a hollow cathedral in the fabric of space, beautiful in its emptiness and profound in what it reveals about the universe's capacity for absence. And in that absence, we find meaning.